looking at page 5, real quick, page 4, again, if there's a repeated, and if there's an eigenvalue multiplicity 3, it's going to take that form. You're still going to have that as your second solution, but your third solution is going to be x, sub 3, so this is going to be your third solution. All right, so you'd have a combination of all three of those. So it would be like your solution would be c sub 1 times x sub 1 plus c sub 2 x sub 2, so all of that plus c sub 3 x sub 3, so plus all that. So it's a very long solution. All right. Now again, if it's a multiplicity 4, you have that. It's going to take on the same form. Just know, it's going to continue with, it goes all the way up to there. So like the next one would be t to the 4th, and then over 3 factorial because it's 4 minus 1. So it's like t to the 4th over 6. So it just keeps taking on that shape. Now, I'm not going to give you any of that big because, in order to even to have a eigenvalue with multiplicity 4, we would need a matrix that's at the smallest matrix would be to get a multiplicity 4 would be a 4 by 4 matrix. It's not fun. You're not going to do that, all right? So, the most I'm going to give you is 3. All right, so let's look at example 7. All right, so what happens if we get complex eigenvalues? So we talked about, just like in all cases when we're solving for differential equations, we get distinct roots, or, in this case, distinct eigenvalues, or we get repeated eigenvalues, or you can get complex eigenvalues. So let's go ahead and look at 34. All right, so we have the system of differential equations, x plus y, negative 2x minus y. So I'm going to put that into the coefficient matrix. And then I'm going to take the determinant. So again, nothing has changed. And then I'm going to go ahead and solve. So when I write out the determinant is lambda squared plus, so that should be plus 1. It looks like a 2. And I'm going to set 2. So I'm going to make sure that, hey, that's a 1. All right. So I get lambda squared plus 1, which, we know that the eigenvalue now is going to be plus or minus I. So we have complex eigenvalues. So what we do is we can plug in our I to get our eigenvectors. And so when we do that, we're going to get you plug it in, we get 1 minus I k sub 1 plus k sub 2 equals 0, and then negative 2 k sub 1 plus negative 1 plus I k sub 2. Now, I'm going to tell you the easiest way to solve these is look for, where do we have like a negative k sub 1 or k sub 2, and we can just move it to the other side. Here, all right, we have that situation. I have a negative 2 k sub 1. I can put it to the other side. So I'm going to show you that. Get rid of all this. All right. So if I do that, I'm going to get negative 1 minus I k sub 2 is equal to, and then we'll say 2 k sub 1. Now, let's make it this easy on ourselves. If k sub 2 is equal to 2, then k sub 1 would have to equal negative 1 minus I k sub negative 1 minus I. So therefore, there's my solution. There's my eigenvector, and I found k sub 2 and k sub 1. Again, check, plug them in there, but it's going to work out for you. So when you have the reason I didn't use the first one, because that's a plus k sub 2, then I have to do a minus on the other side. And I don't want to work with the negative k sub 2. Because I was able to move this negative 2 k sub 1 to be 2 k sub 1, that made my work without, a lot of negatives. So I was able to solve for the eigenvector that way. So we've got one eigenvector. That's great. Let's go to the next one. Lambda sub 2 is equal to negative I. So there's our second eigenvalue. Plug in, we get 1 plus I k sub 1 plus k sub 2, and then negative 2 k sub 1 plus negative 1 plus I k sub 2 equals 0. So again, hit undo too many times. All right, we are going to move that negative 2k sub 1 over to the other side. I don't know why I kept doing it this way, but I'm actually going to move the other one. It's, again, much easier if I say, let's just get rid of that, and we'll continue that to be positive. So we get well, we can make k sub 2 be 2 again. Oops. And if we do that, then k sub 1 has to be negative 1 plus I. Again, check, plug it into the original, see if it works, checks out, and it does. So now we have our solutions, or we have our eigenvectors, and now that we have both of our eigenvectors, we can now just plug it into our solution. So x equals c sub 1, negative 1 minus I, the first eigenvector, then e to the it, and then c sub 2, negative 1 plus I over 2, e to the negative it. All right, now what we're going to do is we want to put these in actual terms of real solutions that correspond to complex eigenvalues. So we really don't want to write our answer this way. We want to write our answer in terms of, a real solution, so without i's. So in order to do that, in order to get to this theorem, what we had to do is we had to use Euler's formula once again. And when we manipulate Euler's formula, we come to this theorem to where all we need is one eigenvalue. We don't need both complex eigenvalues. We only need one. And so the only reason why that is because it repeats and it becomes the same thing. So that's why we only need one. So again, make your work easier. Always take the positive I. All right, so alpha plus I beta. And this is, if we had to do the quadratic formula and got alpha plus I beta. All right, that's going to be a complex eigenvalue of our coefficient matrix A in the homogeneous system, and let b sub 1 and b sub 2 denote the column vectors defined by b sub 1, re k sub 1, and b sub 2, im k sub 1. I'm going to show you what that is. It's not something that's complicated. All right, pretty much what this means is that your vector b sub 1, the column vector b sub 1, is just the real numbers of your eigenvector. B sub 2 is the imaginary numbers of your eigenvector. Right? So that's what your B sub 1 and B sub 2 are. So where K sub 1 is an eigenvector corresponding to lambda 1, our lambda sub 1, so our eigenvalue. So the following two vectors are linearly independent solutions on negative infinity to positive infinity. So once we are able to do this, then once we find the eigenvalue, we're finished. Because then we can substitute into our formulas right here, and then we're done. All right, so what we're going to do is we're going to take the previous example and we're going to find the real solutions. So let's go ahead and choose one eigenvalue. I'm going to choose the positive one. So I'm going to do eigenvalue equals I. I'm not going to choose the negative one. Remember, we have two solutions, but we're only choosing the positive one. So I'm only choosing this one. All right, so I choose that eigenvalue, and so then I write out, beta is going to be 1, alpha is going to be 0, and that's an ugly alpha and an ugly beta. Let me just rewrite those real fast. So we have beta, and we have alpha. They're both, so we have their values. Our eigenvector that we found for this was negative 1 minus I, 2. So B sub 1 is going to be the real numbers, so negative 1 and 2 are the real numbers, so negative 1, 2. Again, you could rewrite this eigenvector to, if you want to put the real numbers over top of one another, so you know what B sub 1 and B sub 2 are. And then B sub 2 is going to be negative 1, 0, because our imaginaries, we have a negative I, so negative 1 corresponds to that imaginary, and then there's no imaginary in that second row, so it's just going to be 0. All right, so we found B sub 1, B sub 2. We found everything. All we got to do now is plug it in and we're finished. That's it. So we're going to plug into the first one, so x sub 1. So again, here's our B sub 1 cosine t minus negative 1 sine t. All right, so there's our x sub 1 times e to the 0t, because alpha is 0, so that's just going to be 1 on the outside. I'm going to go ahead and multiply, so I get negative cosine t, 2 cosine t when I multiply over here, and then when I multiply for the second, I get, since it's minus negative 1, it's going to be plus sine of t. All right, nothing for the second. All right, so there's that. There's x sub 1. Again, x sub 2, plug in. Now again, it's b sub 2 comes first, then b sub 1. So that's why it's negative 1, 0. Cosine t, instead of minus, it's plus, negative 1, 2, sine t, and then e to the 0 t, and then we plug it in, and that's what we get. And so then for our answer, I don't know why I put a bar above there. All right, we have c sub 1 times, remember, it's written this way. Our answer is going to be c sub 1 x sub 1 plus c sub 2 x sub 2. That's why, we have that c sub 1 and that c sub 2 out in front. And that's x sub 1, that's x sub 2. And so there's our solution down at the bottom that's already kind of boxed up. All right? All right. Hopefully you found, hey, that's not too bad. That's actually really easy. All I got to do is find one eigenvalue, and I don't have to solve a system. That's great. Solving systems really it's not that fun. All right? So, hey, we're finished. We're done. There's our answer.